Hello everyone. So today we are going to start the course Automatic Control. About the course, it is a 3 credit course with hours as follows. First hour on Wednesday, second hour on Thursday, and third hour on Friday will be Automatic Control. So in this course, we will be learning about the basics of controllers and control systems. Okay? Let's get into more details of the subject. So automatic control. Okay. This is the syllabus. Okay, we will be taking up some examples of control systems. Open loop control, closed loop control or feedback control. Then different kinds of physical systems and their modeling, block diagrams, stability, poles, zeros, transfer functions, etc. Then we will also see the concept of root lockers, frequency response. We will also try to design some simple controllers like PI, PD, and PID using these techniques. And finally, we will also see state space representation and how to design some controllers, if possible, with state space in state space domain. Okay. These are the textbooks that I will be heavily making use of, especially the first two. The first book is Control Systems Engineering by Norman S. Nice, the 6th edition. And the second book is Modern Control Systems by Bishop and Dorff, 12th edition. The third book has a chapter number 10, in which 4 or 5 case examples have been discussed. So as we progress through the course, we will be making use of chapter 10 from the book number 3. Regarding course evaluation. So this time, 20% weightage has been allotted to each of the quizzes, quiz 1 and quiz 2. So total it is 40%. And remaining 40%, another 40% has been allotted for NSEM exam. And the remaining 20% is given for a teacher's assessment component. So your NSEM exam will consist of both MCQ, multiple choice questions, and numerical problems. Your teacher's assessment component has some assignments and surprise class tests, which consists of multiple choice questions and final, followed by a final viva. So total 100% weightage has been distributed in this fashion. Fine. Coming down. So we will begin the subject. What is that? What do you mean by the term system? System or process or plant. These are the terms that are interchangeably used in the for among the control literature. Okay. If you take some book or some journal papers, you will see these terms interchangeably used to indicate the same thing. System. What do you mean by the term system? System means a group of components or a group of entities which function together so as to attain a common objective. Say for example, you have an automobile. It has its own tires, its own propulsion mechanisms, its own seating arrangement. Inside the engine, there is a fuel system, then braking system, etc. All these things, when they stand alone, is of no use. What's the common objective here? Safe and comfortable travel. But when they are put together and when they operate in a particular manner, then they will attain the common objective of safe and comfortable travel. So system means a group of components or a group of entities which function together so as to attain a common goal. Human body is another system. We have a respiratory system, we have lungs, we have a heart, we have brains. All these things have to work together in tandem so that the human being, the goal of maintaining our body is being attained. So all these are systems. So systems can be of different kinds. Maybe biological system, as in the case of human body, or maybe an electrical system like an electrical power system, or maybe an aerospace system, a launch vehicle, a missile, or an aircraft, right? So umpteen number of systems can be identified if you look around. So in short, if you have a system, there has to be a control in one form or another. Okay, then only it will be of use to us. So before we proceed further, let me discuss something. Okay, so this is the ground. Okay, I'm standing here at point A, right? This is point A, right? I want to hit point B with a stone. Right? So what I will do, I will pick up a stone, I will throw it with some force, right? So initially it may fall here, right? Short of that. Short of that. Okay. So let this point be B dash. Okay. Now I know that the stone has not touched the goal point, which is B. So what I know, so what I will do, I know the initial amount of force with which I applied, I threw the stone was insufficient. Now I will increase the force, right? So say second time I'm throwing and it may come and fall here, B double dash. Okay. Now I have more intelligence. I know I should apply a force whose magnitude is between the first and the third case. So now what happens? It may come and it may fall here. Okay. So outputs can be thought of as of two types. Outputs. Okay. One is the actual output, and the second one is the desired output. Okay. So the purpose of any controller is to make the actual output same as the desired output. What was the actual outputs here? We had two outputs. One was A B dash and A B double dash. A B dash and A B double dash. And what was the desired output? It is A B. Okay. So how can we make the actual output same as the desired output? That is the purpose of any controller or a control system. Okay. So now coming down. So here we have a process or a plan which is to be controlled. Okay. So there is a controller here, and this controller directly cannot make the process to give the desired output. It has to have some intermediate means, and that is called the actuator. Okay, actuator you can say it is a kind of a muscle, right? So the controller will give the command to the actuator, and the actuator will drive the process depending upon the control signal given by the controller. So this signal is called the control signal. That which comes from the controller is called control signal. Control signal. Control output is the control signal. Fine. So that will be given to the actuator, and the actuator will drive the plant according to the control signal so that you get the desired output. And any system that operates on the basis of a timer is an open loop control system. Okay. Say for example, a traffic control system. What happens there practically? Say some 10 seconds is allotted for vehicles to move. For vehicles that are to move in eastward direction. Another 10 seconds is given for vehicles to move in westward direction. Okay. So equal amount of time is allotted for vehicles coming from all the four directions. But it is independent of the vehicle density. Perhaps in one lane, vehicle density may be more than the vehicle density in the opposite lane. So if it was a closed loop control system, then we could have given more time for those vehicles where the density would have been more. But practically, such systems are open loop systems. That means it gives equal time, 10 seconds for vehicles coming from east, 10 for those coming from west, and like that. Okay. And similarly, a bread toaster, right? A bread toaster is another open loop example. Why? Because you will put the slice of bread, then what will you do? You will adjust the knob here. So by adjusting the knob internally, you are adjusting a timer. Okay, so that the time through which time for which heat has to be applied onto the bread piece, right? So I say you have set the knob for 2 minutes. After 2 minutes, what happens? It will automatically stop, right? There is no way or no means to examine the quality of the toast. And if the quality is not of required quality, then there is no mechanism to reheat or to reheat the bread slice. Okay, so this is a kind of open loop control system. Okay, so open loop control system simply has a controller, it has an actuator, and the system is being controlled. Right. So this is simple. Right. This will work perfectly fine provided the conditions are ideal. What do you mean by ideal conditions? For example, when we discuss this throwing the stone case, I have assumed the air is standstill. There are no crosswinds. Suppose that there are crosswinds which are acting like this. Okay, then what happens? Instead of B, it may fall at this point, say B triple dash. Okay, so in this case, air crosswinds, they are called disturbances. So the crosswinds, they are called disturbances. Okay, so in the case of this, in the presence of disturbances, open loop plants fail. Okay, because there is no mechanism to check what is the output, to sense the output, and to feed it back, and to compare with the desired profile. Okay, so in the case of disturbances, open loop control systems will fail. Okay, so now we have what is called a closed loop control system, and it is like this. So what's the advantage here? Here, the output will be sensed through a sensor, and it will be fed back so that it can be compared with the command signal. Okay, and error will be generated. So the controller will be taking the error as the input signal to it, and it will generate a control signal so that the actuator will eventually drive the process or the plant to give the desired output. So keep in mind, this control signal is also this desired output response is also called command input or reference. Okay. Reference, right? Why this is called desired output response? Because it has to follow a particular command, right? It has to follow a particular command. So eventually this error. So what's the error here now? This command minus the output signal. Okay. So error is 0 means what? Command equal to actual output signal. So we want the actual output to be the desired output. That is why this is called the desired output response. All these three terms are one and the same. Okay. So it utilizes an additional measure of the actual output, that is called the feedback signal, and compares it with the desired output or the reference input or the command signal, right? This signal is error signal is also called actuating signal. Actuating signal. Okay, error signal is also called actuating signal, right? So always the controller will act upon the error signal to provide a control signal. So this control signal will be taken up by the actuator. What do you mean by actuator? Actuator actually represents the muscle. Say, for example, you have an antenna whose direction is to be oriented towards a particular satellite, right? So there's a controller. So controller will give the command signal. To whom? To antenna? No, if the controller directly gives the command signal to the antenna, it cannot turn by its own. So instead, there will be a motor. Okay. So the output from the controller will be given to a motor, which will drive the antenna to the desired orientation. Okay, so there the electrical motor acts as an actuator. Okay, so you will see different kinds of actuators in due course of time. Okay, so here we can see the error or the actuating signal is dependent on the output signal. Okay, error or the actuating signal. What is that? The reference input minus the actual output. Whereas in this case, what is the error signal? Error signal is independent of the output. Okay, whatever command you give, it will simply work accordingly. Blindly, it will work accordingly. Okay, there is no output sensing, no comparison with the input, and there's no feedback. Okay, because of which, if any disturbance comes into the picture, system will drift away from the desired output. Okay, so this is what I explained just now. So in the process of disturbance or in the process of measurement noise, right, the closed loop system will give the actual, will give the desired output. Okay. So it is the process of disturbances or uncertainties that warrants the need of a feedback or automatic control. Otherwise, there is no need. An open loop control is perfect, right? It's more economical also, right? An open loop control is perfect and economical provided you have ideal condition where there are no disturbances, no unwanted signals, or there are no uncertainties. Okay. Otherwise, you have to go for an automatic control or a feedback control system. Now, in some books, the actuator and the process will be clubbed together as a single block, and they call that as a plant or a system. So in this course also, we will throughout follow this notion, right? When we represent a block by controller, it is implied that the actuator is also embedded within that. Okay, so this is the controller block, this is the plant, and here is our feedback signal. Now, what is this input filter here? For example, in the case of bread toaster, I told you we'll be setting the no. Okay, that's a physical quantity that should be translated into its corresponding electrical signal. Okay, so the input filter does that job. Okay, it will convert physical signals into appropriate electrical signals. Then only comparison can be done and it can be driven. Okay, so it is necessary to let the disturbances affect the system. Why? Because you have no control over disturbance. Disturbance means what? Unwanted signals. Okay, so and the disturbance should affect the system, measure the actual corrupted output, and inform the controller and let the controller react to it. Okay, so even in the presence of disturbances, a closed-loop controller can give perfect operation. Okay, that's the advantage of having a closed-loop system. Now, as an example, how we are steering an automobile, right? So the driver will be continuously driving the automobile, right? So there will be a desired path. So if you are deviating from that, the driver knows the car is deviating away, so he can bring it along the desired course of travel. Okay, that's what is shown here. So the black one is the desired direction of travel. So manually, the driver will adjust the steering mechanism, the brakes, and everything. Okay, and accordingly, it will follow this desired trajectory, right? But in a driverless car, what happens? The black trajectory and the blue trajectory will be perfectly the same because it will be modeled in such a way, right? It will automatically take care of the course of travel. Now, this is the example that I spoke some time back. Okay, you have a rotating disc upon which an antenna is situated, right? So in an open loop case, what happens? You are giving some speed setting. Okay, how it should be driven, right? So whether the antenna is pointing correctly or whether it just over exceeded, it doesn't check. Okay, but in the case of a closed loop system, there will be a sensor called tachometer. What's the purpose of tachometer? To measure the speed. It's a sensor that will sense the speed of a system, right? So the tachometer can sense the speed and it can feed it back to the desired signal. Error will be generated. Controller will accordingly will generate a control signal. It will drive the plant or the rotating disc. Okay, in that way, accuracy can be achieved. Now, control feedback exists in almost all systems, as I told before. For example, the human body, right? There are many biological feedbacks. So this is one example. The insulin, how the insulin is being generated within the body. Suppose you have suppose this is the insulin profile for a healthy person, right? So in the morning, when you have breakfast, it will start shooting up slowly, and then it will and then it will come down. In the meantime, in the noon time, you will be having your lunch. Again, it starts slowly building up the insulin level. And same in the case of dinner time. It keeps on repeating. This is the pattern. Okay, but in a diabetic person, this doesn't happen. Okay, because a diabetic person means one who doesn't have enough of insulin production in his body, right? So what's the control goal? We have to regulate the blood sugar concentration in a diabetic person. What's the variable to be controlled here? Of course, it is the blood glucose regulation concentration. What is the design specification? We have to provide a blood glucose level similar to that of a healthy person. Okay. Now for that, again, two strategies: open loop control and closed loop control. So in open loop control, what happens? You are simply administering the insulin level. Okay, there will be a motor pump and a valve will be there. You will just administer it when it is programmed, right? So, but sometimes it may be of sufficient quantity. Sometimes more insulin might be administered. So in open loop control, there is no mechanism to check whether what we are delivering is of the adequate level or not. Okay. Whereas in a closed loop control system, you have a sensor to sense what is the blood glucose level in the diabetic body and whether the insulin that we are injected is sufficient or not. So that will be compared with the desired blood glucose level. and then error will be taken care of, and accordingly it will attain the desired glucose level. Okay, so from accuracy point of view, always a feedback system will stand higher than on top of open loop control system. Now there are multivariable control systems as well, where multiple variables are to be fed back. Okay, multiple variables are to be fed back, compared, and controller has to act on such signals. For example, the heart rate control. Okay, even though the heart rate is to be controlled, multiple organs are involved, like the lungs, the brain, the vascular system, and so on. In fact, this is a simplified model. Okay, there are many factors. Okay, so all these signals have to be controlled so that you have appropriate heartbeat or heart rate control. Okay, unmanned aerial vehicle, it's a complicated case, right? So it may be an unmanned aerial vehicle, or it may be a fighter aircraft. So fighter aircraft means it should be more agile, right? It has to maneuver in many different possible ways, not like the way in which a normal aircraft is traveling. Okay. Then there may be loops within a loop. Such systems are called multi-loop feedback systems like this. Okay, there's a loop within a loop. There's an inner loop, there's an outer loop. Okay, it's a simple case. In a large vehicle, there may be many such loops like that. Okay, so it depends on the system and its complications. Now, this is a simple sketch of a incubator for hatching eggs. This was devised sometime in around 1600s in that time period by a man called Rebel. This is to hatch the eggs here. You can see the eggs are kept inside the chamber. And here there's a water in this chamber, which will get heated up by the fire which is given here. Here you have an alcohol. Alcohol is filled in this tube, which is connected to a mercury chamber, and these levers are connected to this riser. Okay. So what happens? Temperature is high. Then what happens? This alcohol expands, and then what happens? This will be pulled down, and this inlet will be opened. So cold air can flow into the chamber, and the temperature can be maintained, or vice versa. Okay. So accordingly, a desired temperature can be set. So wherever there are cause and effect relationships, you can say feedback exists. Okay. What are the advantages of feedback? It can improve stability. Okay. Or it can be even harmful if not used wisely. Okay. So you have to use it carefully. It will reduce the effect of noise and disturbance on system performance. Or in short, it makes the system insensitive to noise and disturbance. Okay. Similarly, parameter variations are also not affected if you are employing feedback into your control system. So what's the summary? Summary is that control is necessary to make a system variable to adhere to the reference value, right? Now suppose you are giving a constant reference input. Okay, say it has to maintain a velocity of say 30 kilometers per second. Some example. Okay, it doesn't change. 30 kilometers per second is constant, right? Then such systems are called regulators or regulating systems. Okay, it's a system which is designed to maintain an output fixed, constant, okay, independent of the disturbance is called a regulator. For example, a fan regulator, right? When you turn the knob and put the position and corresponding to position number 3, what happens? The fan will keep on rotating at a constant speed. Whether you open the door, whether you keep open the windows open, it is immaterial, right? Once it is kept at knob corresponding to position number 3, the fan will keep on rotating at a constant speed. Such systems are called regulators. That is why it is called fan regulator. Okay. But if your reference is time changing, say for example, you want to track an enemy aircraft, right? Enemy aircraft is not constant, it keeps on changing its profile, right? With respect to time. So in such cases, you call the control system as a tracking control or a servo mechanism, or a tracking control system, tracking problem. Okay. So if you are following a time changing reference, it is called a tracking problem. If you are following a fixed output, independent of the disturbance, then you get what is called a regulator. Okay. Now in open loop control, as I said before, the actuating signal or the error is independent of the output, whereas in a closed loop control, the actuating signal or the error does depend upon the output through a feedback, right? So a closed loop control system consists of a process or a plant whose output is to be controlled, an actuator whose output causes the process to change, a sensor to sense the plant output, and as I said before, an input shaping filter, okay, which will convert the reference signal to electrical form, and the controller, which will generate the control signal. Okay, so this is the takeaway from today's class. Fine. Now I would suggest you to try some more two examples. Few examples here. An aircraft's active control. So this is an aircraft, right? So as you know, there will be 6 degrees of freedom for a body in air, right? 3 linear and 3 angular, right? So the angular movements, they are the roll, pitch, and yaw. Okay. So the roll axis is shown here like this, right? This is the roll axis, and movement about the roll axis is called the roll angle or the roll movement, right? To control the roll, aircrafts are having some controllers called ailerons. So if you have seen aircrafts, at the back end of their wings, there will be some moving surface. They are called aileron, and they are used to control the roll angle of an aircraft. So what you have to do, you have to identify, okay, you have to draw a functional block diagram, right, for a closed loop system that will stabilize the roll motion, right? So you have to further, you need to identify the input-output transducers, the controller, and the plant. Okay, so you can try this as one of the examples. Another example, a temperature control system, right? You have to draw a functional block diagram, identifying the input and output transducers, the controller, and the plant. Okay. Then another example, especially in the present pandemic times, it is related with HIV or AIDS problem. Okay. So you have to identify the blocks representing the controller, the system under control, transducers, and so on. Okay. You can refer to Google or you can refer to some encyclopedia. Just try building up a closed loop block diagram. Okay, just try building up a block diagram for us. Now, there are many variables in the human body that are fed back and are controlled, like blood pressure, blood sugar concentration, heart rate, and so on. Okay, so you can try drawing a block diagram for all these things. Fine. You may have to refer to some encyclopedia or some textbook on human physiology. Maybe in this context, I forgot to tell you about the brain chip. You might have heard of our Elon Musk is trying to build up a chip that can be interfaced with the human brain, so that the computers and humans can directly interact. Okay, so so all these are after effects or offshoots of what you call a feedback control system. Okay. Then when a person is under stress, again the hypothalamus, which is situated in the brain, will secrete a hormone, right? How to regulate that? You can think of, as another biological example, feedback example, you can think of building up a block diagram for this closed loop system. And lastly, you have to identify what are the sensors that are used to measure this temperature, liquid level, pressure, and so on. Okay, linear velocity. So all these things all these are mechanical quantities or physical quantities. They should be converted into appropriate electrical signals. And that's what the purpose of a sensor or a transducer. So try to identify transducers which will convert temperature into the corresponding electrical output, liquid level into electrical output, and so on. Okay. So with this, we will stop here. Thank you.